Okay, if no, then let's look at some non-ideality of the diode, right? We talk about diode, but actually this is not the real diode. We actually have some resistance for a real diode. Okay, so when you apply VD, you actually apply VD to here. So what is the real equation? I, remember, is IS exponential VD divided by V, I forgot what we call it, phi t, right? Phi t minus 1, correct? But now the VD is not applied to the diode because I have some parasitic resistance. So it's going to be I times Rs, or because I have two of them, I say 2I times Rs. Right? So in a real diode, you actually have this parasitic resistance. So why do you know why we have this resistance? Any idea? There are two sources. One is in the neutral region. What is the meaning of the neutral region? We always just look at this diode in this way, right? So in this region, and here, you have resistance. This is the neutral region resistance. Because after all, this is just a piece of conductor or resistor before you reach the depletion region. So of course, you have this resistance. Second is the contact resistance. This is something very important nowadays. Well, you have an N plus, and then you say this is P. This is a diode. But how do you connect to here? You actually need a metal. For example, I don't know, aluminum or copper. You are contacting different material. Here we have a contact resistance. Because for any material touching each other, they have a inhomogeneous interface. So you have contact resistance. Then you say, wow, that should be very small, right? If I really press it really hard, I use very good doping. You're right, they're super small. Talking about 10 to the power minus e ohm cm squared. But in nowadays device, they are so good. Contact resistance becomes very important. So although here is only for diode, remember, this is also for transistor. And that's why we cannot just optimize the transistor. If I make a transistor really good, but you increase the contact resistance, no one is going to use this technology. So same for you as a circuit designer, you need to pick the right technology for your purpose. Okay, any questions? Well, another non-ideality is earlier we say that the I is equals to exponential VD over phi t minus 1, right? If we take the log, we get a slope like this. But in reality, we have an n here. If it is ideal, n equal to 1, then it's ideal. But in reality, you don't get that. Usually 1 point something. When it is 1 point something, it means that I take more time to increase my current, right? This can be due to other things you might, anyone can guess what can be the source of this non-ideality from your device physics class? If you don't know, that's normal. This is really device physics, right? That can be due to the traps assistor leakage. Okay, so the leakage is not just a simple leakage for full fermionic emission, but I just give you an example. No worry about this, but learning more is better. Okay, and then the final thing is that even if I keep increasing the reverse bias, is it going to be zero leakage? a very small leakage. Based on this equation, when I go to very negative VD, I should only have IS, right? I should get about negative IS. But you see that when it is large enough, the current increases a lot. So there are two types of reasons. One is that when you have a very huge reverse leakage, you have something like this. This is negative, this is positive. Well, electron cannot go here. No way, too high, right? But I may have one electron from here. What happened? This electron will just move. When you see this such a huge electric field, it gains a lot of energy and will suddenly drop the energy and create an electron hole pair. And this hole is going to move up, this electron move down, and this hole is going to generate another electron hole pair also later. Okay, so this is 1, this is 2, this is 3. And you keep triggering, keep multiplying. And this is the so-called of avalanche. This is just like the avalanche on the snowy mountain. Starting with one little snowball, it keeps amplify, and eventually the whole mountain snow collapse. And that is so-called avalanche breakdown. Another is so-called tunneling. When you have such a thin barrier, although I don't have electron going down, but I have plenty of electron at the hole, at the valence band that can tunnel to here, and then it becomes a hole, right? Because it's very thin, there's a quantum mechanical tunneling. Quantum mechanical tunnel meaning that classically, the particle doesn't have energy to go over the wall, the barrier. But when the wall is so thin and the particle's mass is so small, it has a finite probability to go through the wall, which it cannot if it were classical. Okay, so these are the three non-ideality. Any questions or comments?
So this tunneling, it's based on probability, right? Like
exactly.
It's not guaranteed that it's gonna happen. Like for example, for 1 minute, if you have, actually you don't even need to bias the diode, right? If you
you need to bias the diode so that it is thin enough.
So let's say it's thin enough for like 1 minute, considered like just 1 minute time frame. Like it might tunnel in that time frame, it might not.
Correct, but however, I have trillions of electrons or quadrillions of electrons in the valence band. So yes, for each of them, it might tunnel or not tunnel within 1 minute. But for since I have quadrillions, 10 to the power, or even 21 electron, so I am sure that some will tunnel through there. If it doesn't tunnel, that will be a very, very rare event. You see what I mean?
Yeah.
Yeah. So from macroscopic view, you always can measure the current. So that is a very good question, right? But for a particular electron, it might or it might not tunnel. You are right. Any other questions? Someone just want to comment, right? Or okay, if no, then let me move forward. Also want to say that the diode's equation, of course, depends on temperature. Why? First of all, phi t is kT over Q, right? Definitely when temperature increase, phi t increase. As a result, the current will decrease. But at the same time, IS also depends on temperature by Pn0, Nn0. They actually depends on temperature. When temperature increase, IS will increase. Okay. So in general, ID will increase, right? So in general, overall effect is this. We are not going to prove it, right? It is lengthy and also no need. For the same ID, VD decreased by 2 millivolt per degree C. Okay, so it means that I have a larger current for the same voltage if I increase the current, right? So this is just a rule of thumb. Okay, have an idea is good. Yeah, if you are a circuit designer, you have an idea. Okay, all the for the same current decreased by 2 millivolt, right? And then you can also calculate for the same voltage how much current is going to increase when we increase the temperature. Is that okay? Right. So why I say all these things, but they are all relevant, right? So this is a diode model, SPICE model, and you do see that these are the equations they implement in SPICE simulation. For the simple one, talk about IS, the N, non-ideality factor, series resistance, junction bias, grading M, junction potential. Transit time we did not mention is related to how fast the whole, how fast you can remove the excess carrier. But I won't go into detail here. We're not doing device physics. This is related to how fast it can switch. Okay, so all of this should be very straightforward to you now. Okay. So this is